Right, let's look at some projectile motion questions. So here we've got a projectile being launched. It's going to follow a parabolic curve all the way until it hits the ground again. What we want to know is the distance it's travelled, or what we call the range, the horizontal distance. Just a couple of points. Halfway along, right at the top of this path, our velocity equals 0 meters per second. And the acceleration on a projectile is always negative 9.8 meters per second downwards. That's, remember, the one force that's acting on the projectile is gravity, and that force is producing an acceleration of negative 9.8. That's the only force, and it's always constant, negative 9.8 meters per second downwards. Okay, so we're given a vector with an angle and magnitude. So what we can do is we can find out the components. These components are going to tell us the vertical and the horizontal velocities. Now, before we can actually do that, it's best to draw a wee triangle. So here I've sketched a triangle of so I can get a look of what my initial velocity for vertical is and my velocity for horizontal. Remember, when I work out the velocity for horizontal, because it never changes and it's constant, it's just the velocity. Okay, so if I want to work out my initial vertical velocity here, I notice that it's the opposite side, and we have the hypotenuse, so we're going to use the sine rule. We carry out the calculation and we get the answer, 14.4 meters per second. The same again if I want to work out the velocity, the horizontal velocity here. It's the adjacent and the hypotenuse, so I'm going to use the cosine rule. And I get 19.2. Okay, so just have a check of these. If this is a sharp angle here, I expect to have my horizontal one being longer than my vertical. And that's exactly what I've got here with the data. So I'm quite happy at the moment that this data that I've got is close to what I would expect. So the next step we want to do here is find the time. Now, in order to find the time, we can make a wee simplification here. We can find the time halfway along the motion. And if we find the time halfway along the motion, it makes calculation simpler, because we know that our final velocity equals 0. And in the end, we can just double our time to get the time along the full length of our projectile motion. So we'll use this equation here, Vf equals Vi plus At. We're making the assumption, remember, because we're halfway, that Vf is going to equal 0. So we put that into the calculation. We're going to rearrange the calculation so that time is the subject. It's on one side by itself. Okay, so we move the Vi across. It was positive here, so it becomes negative on the other side. And then what we're going to do next is move our acceleration to the other side. At the moment it's multiplying, so when we take it over the other side, it's going to be dividing. So we get time equals negative initial velocity divided by acceleration. We chuck the values in, and we get the time, 1.47 seconds. Remember, however, that is the time it takes to get halfway along the path here. So our actual time is 2.94 seconds. Okay, so this is the time that we have for our vertical motion, that is for the projectile to go all the way up and all the way down again. That is also exactly the same time it takes to get from the start to the end horizontally, because we're measuring the same object, so it's going to take exactly the same amount of time. Because now we know our time and we know our velocity, we can work out the distance that our object has travelled horizontally, and this will give us the range. Now, when we're working out the horizontal distance, we always just use this simple equation, the velocity equals change in distance over change in time. The reason we're able to use this equation is our velocity is constant, it never changes. We never use this equation with our vertical velocity because it's constantly changing. Okay, so we just put the data in here. We've got, let's rearrange it first. Our distance equals our velocity times our time. we take our velocity from over here, 19.2, and our time, which is 2.94, and we get the answer, 56.4 meters, which, of course, we round to 56 meters, two significant figures, because our initial data was given to two significant figures. Okay, let's look at another problem. So this one here, again, projectile motion, it's undergoing a full range of it's undergoing a parabolic curve here. It's however, it hasn't given us the initial velocity. So we're going to have to try and work out the velocities from the time given. Now we want to simplify this equation, the situation a bit again. So first thing we can do is say we know what the acceleration is. Remember, negative 9.8, always negative 9.8. We know, and remember that's in the vertical direction, going downways. And we know that halfway along our velocity is going to equal, our vertical velocity is going to equal 0 meters per second. So knowing that the acceleration and knowing the final vertical velocity, we can actually we know the time as well, 2.35 seconds, because it's half of the total time. When final velocity equals 0, half the total time is 2.35. So knowing those three bits of information, we can use this equation here and we can find out the initial velocity. So we're always looking for an equation where there is one unknown that we want to find out and we know the other three things. So we're going to substitute in the 0 here for our final velocity, rearrange the equation just as we did in the last example, VI equals negative AT, and substitute in the values, getting an answer of 23 meters per second. Okay, so that is our initial vertical velocity. Now we have to find out how far it travelled. Okay, so here, well, let's, while we've got the initial velocity here, the vertical velocity, let's find out the horizontal velocity using trigonometry. So here we've got opposite and here we've got adjacent. So we're going to use a tangent, okay, and we're going to get V equals 23 divided by tan 65. And our velocity equals 10.7 for our horizontal velocity. We're going to look at the wee sketch we've drawn and see if that number seems realistic, and yeah, it does, because my horizontal velocity looks about half of my vertical velocity. Right, we've got two velocities. We can start working out the distances. Let's work out the vertical distance. Vertical distance, we know the time, okay, to get to the top. We know the acceleration, we know the initial velocity, and we know the final velocity. So there's a few different equations we can use. In this case, I'm just going to use this one here, d equals VIT plus half AT squared. Okay, and here we go. I chuck all the data into that equation, and I get the distance of 29 meters. Right, and last thing I want to do here is calculate the vertical distance. Remember, this one here is usually straightforward, or always straightforward. We just rearrange this velocity equation to the change in distance equals velocity times time, and chuck in the data, and we get the distance here, 50 meters. Again, I have rounded to two significant figures because my initial data was to two significant figures. Now, steps 2 and 3, okay, we could have done in a different order. We could have done step 3 before step 2. It would have made no difference here. And we also could have worked out the distance in step 3 using a different equation. One of the things about kinematic equations is you can get the same answer from using different combinations of equations. So as long as you get the final answers of 29 meters and 50 meters, you're all good. Okay, I hope this has helped, and goodbye.